Good afternoon, everybody. Welcome to an exciting afternoon of Chem 1105 with your host, me, Dr. White. All right, today I'll be going through the review for test 4, which is coming up this Thursday. But before I do, let me remind everybody who needs reminding, do the labs, hand in the labs. I'll probably put out an email tomorrow. Well, I'll extend the deadline a little. But if you don't do labs, and a lot of you haven't done a lot of labs, you're going to really lower your grade. I've seen students in the past who haven't done a lot of labs go from 1 or 2 letter grades lower than what they should have gotten. At least one, maybe even 2 letter grades lower. That's like going from an A to a C or a B to a D. You don't want that to happen. I don't want that to happen. So please do the labs. All right. Now, test number 4 will be on the chapter dealing with acid and bases, and the chapters dealing with my favorite, because organic chemistry, but I'm an organic chemist. All right, let's get to work. And as you see on your screen right now, Chem 1105, test number 4 review, or review test number 4. This, what you're seeing, is in the lecture folder of Blackboard, cleverly named Chem 1105 Test 4 Review. So you can find us. All right, let's get started. Things you should know about acids and bases. You should know a Bronsted-Lowry acid is any substance that can donate a proton, proton H plus. So what is a Bronsted-Lowry acid? A proton donor. Here, take my proton. I'm a Bronsted-Lowry acid. You should know this, especially when I put something in red. You should know that. Next, what's a Bronsted-Lowry base? It's any substance that can accept a proton from another substance. In other words, it's a proton acceptor. Bronsted-Lowry acid, here, take my proton. I'm a proton donor. I'm an acid. Bronsted-Lowry base, give me your proton. I'm a proton acceptor. I'm a Bronsted-Lowry base, or just base. You should know that. Now, you should know the structures of some basic acids and bases. HCl, hydrochloric acid. H2SO4, sulfuric acid. HNO3, nitric acid. If I put these structures on a test, you should be able to identify they are acids. And by the way, in your stomach, mine too, we have cells, and I think this is one of the miracles of life in my brain, that make hydrochloric acid, HCl. And your body uses the HCl, hydrochloric acid, in organic chemistry from Mother Nature to break down your food, your proteins, your carbohydrates, and your fats and oils into molecules your body can use. Now, bases you should know, remember acid proton donor, base is a proton acceptor, NaOH, sodium hydroxide. I'm not going to ask you to learn the names, but you should know that structure is a base. KOH, that's potassium hydroxide, that's the base. And NH3, ammonia, that's the base. Now, one of the more, I sneezed on the truth. One of the more important things in life is water. And water has some very unique properties. And one of them is it can dissociate, react with itself. And Here we have water reacting with another water molecule. This is called an equilibrium. And most of it stays as water on the left, but a little bit can go to the right to form H3O plus, the hydronium ion, and the hydroxide OH minus. And because it's an equilibrium, and unfortunately, we don't teach equilibrium in 1105. I teach it when I teach 1211, but that's a different course. We have what's known as an ionization constant. This is always the same number. And for the dissociation of water, K is for constant, W for water. Actually, it's after me, KW, Dr. Kenneth White, I wish. But long before I was born, a name that was developed. But KW, yay, is hydronium ion concentration. When you see a formula in a bracket like this, that's molarity, moles per liter, the concentration times the hydroxide equals, and this should be 1.0 times 10 to the minus 14. And this is for room temperature, 25 degrees C. Other temperature changes, but we won't get into that in this class. Now, let me remind you, at the end of test number 4, the last page or two, you'll see important information. And notice here, I have KW equals hydronium ion concentration times the hydroxide equals 1.0 times 10 to the minus 14. Like I've said all semester, I've cut way down on memorization. I'm testing your knowledge of chemistry. I'm not testing your knowledge of chemistry and your memory. But again, this is important information. You can go look and see what you'll be given is in the lecture section folder of Blackboard, and it's called Important Information Test number 4. Now, when we talk about in our everyday life, whether you're a chemist or other professionals, or just doing your swimming pool even, there's terms acidic, basic, and neutral solutions. And you should know an acidic solution, the hydroxide concentration is higher than the hydronium ion concentration is higher than the hydroxide. One way of thinking of it, this concentration is greater than, that's what the symbol is, greater than the hydroxide. So that's an acidic solution. And you should know this. Next, the basic solution, the hydroxide OH minus concentration is greater than the hydronium, just the opposite. And sometimes it's called an alkaline solution, alkaline batteries inside is a basic solution. Used to be acidic, and some batteries still are. And finally, a neutral solution, the hydronium ion concentration is equal to the hydroxide concentration. So, acidic solution, hydronium ion concentration greater than the hydroxide. Basic solution, hydroxide OH minus greater than the hydronium OH3O plus concentration. And neutral solution, the hydronium ion concentration is equal to the hydroxide. And if you look it up, you can find out the solution, the liquid is in your stomach, because you're drinking a lot of water. Hopefully you're drinking the water you're supposed to every day, is acidic because the hydronium ion concentration is greater than the hydroxide, also because it contains hydrochloric acid. So acidic, hydronium greater than hydroxide, basic, hydroxide greater than hydronium, and neutral, hydronium equal to hydroxide. Now, it turns out, if I said the hydronium ion concentration is this number, the hydroxide is that, then you got to think if this is scientific notation, which is the greater number, that's a lot of work. And chemists like to be lazy, especially organic chemists. I know I'm an organic chemist. So someone came up and said, one day I'll look up who did, called the pH concept. And the pH scale is a small number that is used to specify molar hydronium ion, that's H3O plus concentration in an aqueous solution. And by definition, pH equal minus the log of the hydronium ion concentration. Now, I didn't take the time to ask you in this course to learn how to use logarithm on your calculator. I know how to do that, but my special gift to you this semester is if the hydronium ion concentration is equal 1.0 times 10 to the minus x, then the pH is x. If H3O plus concentration is 1.0 times 10 to the minus x, then the pH of that solution is x. And let me point out important information, test number 4. I'll give you that. And I'll also say, remember, the hydronium ion concentration is 1.0 times 10 to the minus x. The pH is x. Now, how does this pH help us with, is it acidic, basic, or neutral? Good question. Thank you. Well, there's the pH scale. And notice I say important. And let me make it even more clear. And know this, the pH scale goes from 0 to 14, never less than 0, never greater than 14. Anything at pH 7 is neutral. Anything below 7 is acidic. The lower it is towards 0, the more acidic it is. And anything above 7 is basic. The closer to 14, the more basic it is. Again, 7 is neutral. Below 7 is acidic. And above 7 is basic. Know this. Of all the things I'm going to teach you this semester, this is probably the most important. Notice I have here, the lower the pH, the more acidic, the higher the pH, the more basic. By the way, this is a logarithmic. And the difference between a pH of 6 and 7 is 1.0 times 10 to the 1 power of the concentration, 10 times difference. So each number is 10, but I won't ask that on the test. But you should understand the scale. All right, let's look at a couple from the practice problems. Chapter 7, acids and bases. This is in the folder on Blackboard, practice problem answers. And what is a Bronsted-Lowry acid? A proton donor. What is a Bronsted-Lowry base? A proton acceptor. And as I said, you should be able to identify the following as acid base. I threw in sodium chloride, NaClC salt, and like AHCl, hydrochloric acid. BNaOH, sodium hydroxide, is a base, and so on. Now, let's look at number 4. If a solution has the hydronium ion concentration of 1.0 times 10 to the minus 3, what is the pH of that solution? And is it acidic, basic, or neutral? Well, we're trying to find pH. We're given the hydronium ion concentration is 1.0 times 10 to the minus 3. Important information, you know pH is minus the log of the hydronium ion concentration. We'll put that in there. When the hydronium ion concentration is 1.0 times 10 to the minus x, pH is X. This is given to you. So what's X? 3, because it's 1.0 times 10 to the minus X. X is 3. The pH is 3. Is this acidic, basic, or neutral? Well, hopefully you have learned the scale. pH 3 is less than 7, therefore it's acidic. Oh, let's do another one. These are fun. Let's do number 6. If a solution has the hydronium ion concentration 1.0 times 10 to the minus 12, what is the pH of the solution, and is acidic, basic, or neutral? And as you've learned this semester, when I do a word problem, yes, relax, relax, take a deep breath, let it out. Yes, it's a word problem because it's got words that are making you figure out something. Word problem. All right, what are we being asked to find? What is the pH? What are we given? The hydronium ion concentration is this, 1.0 times 10 to the minus 12. Now, as you saw, important information, pH equal minus the log hydronium ion concentration. We put in the hydronium ion concentration. When this is 1.0 times 10 to the minus X, the pH is X. In this case, X is 12 because it's minus X. Remember that. And is that acidic, basic, or neutral? Hopefully, like it says on the screen, you know this, that when the pH is greater than 7, it's basic. And therefore, it's basic. Oh, I got this right. All right, let's look at another problem, but a little more complex. If a solution has OH minus hydronium ion concentration, hydroxide ion concentration, let me get it right, hydroxide ion concentration 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? Well, I have the pH, that's what I'm trying to find. I'm given OH minus concentration. Remember, when it's in brackets, that means concentration is 1.0 times 10 to the minus 3. And I know pH is, 1.0 times 10 to the minus, minus the log of the hydronium ion concentration. Let me do that again. pH is minus the log of the hydronium ion concentration, H3O plus. But we don't have that. What do? You do 2 steps. The first step is you have to convert OH minus concentration to H3O plus concentration. How do we use that? From Kw, the ionization constant, which is hydronium times hydroxide concentration equals 1.0 times 10 to the minus 14. And in case you forgot, you see that in test number 4, information. So now, how do we solve for hydronium ion concentration, H3O plus? Well, I have to get it alone on one side. So how do I get rid of OH minus concentration? Divide by it. Anything divided by itself becomes number 1, which means it's gone. Whatever you do to one side, you do to the other. So this becomes H3O plus, and it's equal to this, hydronium 1.0 times 10 to the minus 14 divided by the hydroxide concentration, which I have. I put it in there, use my calculator. You all, hopefully by now you all know how to do scientific notation. Not come to my office hours for help before test number, hold on. Two or three more rings, and then my answering will pick it up. Stop. I have a Bluetooth phone hooked up to my cell phone. Years ago, I cut my landline. I didn't need that in a cell phone. Anyways, we put that in there and we get the hydronium ion concentration is 1.0 times 10 to the minus 11. Are we done? No, we're trying to find pH. So you need a second step. Second step, you take the H3O plus hydronium ion concentration and convert it into pH. How? pH equal minus the log of the hydronium ion concentration. Remember, that is in important information, test number 4. I'm gonna get that finger fixed someday. And we put that in there when H3O plus is 1.0 times 10 to the minus X. The pH is X. In this case, X is 11, the pH is 11. And the answer also you have to know is that acidic, basic, or neutral. And you've learned and know this chart. Below 7 is acidic, above 7 is basic, at 7 is neutral. And we're at 11, that's above 7, so it's basic. And if you look at the problem set, I have a couple more here for you to look at on your own. Now, while we're talking about acid bases and what they do to pH, let's look at number 10. What happens to the numerical value of the pH of a beaker of water at pH 7 if you add a few drops of concentrated NaOH solution? Well, that's a base. And a base, pH 7, is going to make the pH go up, increase. The numerical value will get larger or increase. Now, let's look at 10b. What happens to the pH of a beaker of water at pH 7.0 if you add a few drops of concentrated H2SO4 solution? I don't know why I have solutions. It should just be solution. But anyways, well, I found a mistake I haven't seen in years. But you haven't seen it all, or I would have corrected it. H2SO4 is an acid. What does an acid do? It lowers the pH, makes it acidic. So the pH decreases or gets lower. So whenever you add a base to a beaker of plain water at 7, the pH will increase. Whenever you add an acid to a beaker of water at pH 7, the pH will go down, decrease. Now, an interesting concept is called a buffer. And I'm not going to go in this class how you make buffers, but it's a solution that resists major changes in pH when small amounts of acid or base are added to it. So if you have a buffer solution and you add a small amount of acid, the pH doesn't change. If you have a buffer solution and you add a small amount of base, the pH doesn't change. By the way, your blood is buffered to keep the pH around 7. If it goes too far away from that, guess what happens? You die. And Mother Nature has your blood buffered, which is a good thing because I don't know about you, but I'm glad I've got my pH of my blood correct so I can stay alive. If you look at number 11, what happens to the numerical value of a pH of a beaker of, and it's important, a buffer solution if you add a few drops of a dilute acid solution? The pH stays the same, no change. What happens to the numerical B value of a pH of a beaker of a buffer solution if you add a few drops of a dilute base? Well, it's a buffer solution and the pH stays the same. Now, an important concept is neutralization. When you add an acid and base, equal amounts, the pH, whether if you started with it was acidic and you add a base, goes toward pH 7, neutral. If you have a base and you add an acid, that neutralizes the base, so the pH goes toward 7. Now, at neutralization, pH 7, moles of acid in that solution equals moles of base. And I gave you a special gift. Instead of having you calculate it, I gave you this formula. Milliliters of acid times the molarity of acid equals milliliters of base times the molarity of base. And throughout industry, the chemical industry, cosmetics, a lot of things, being able to identify and titrate something, neutralize something by adding an acid or base, it's called a titration, helps determine very special properties of materials. And titrations are very important. If we go to important information, test number 4, at neutralization, I give you moles of acid equals moles of base, and I give you that formula I just mentioned, milliliters of acid times molarity of acid equals milliliters of base times the molarity of base. I worked at one company where I was the laboratory manager, charged both research for North America and the quality control lab of this chemical plant located with the research labs. It's on the south side of Chicago, 47th and Racine. And every morning, people in the lab did many titrations to the point where I actually was able to develop, with the help of a company, a machine that did it automatically and allowed the chemists to do other things too. By the way, that machine cost $50,000, but the man hours it saved paid for itself in 4 months. Yep. Chemistry can be fun. All right, let's look at a titration problem. 10 points. Yep, 10 points. If you have to add 1.35 times 10 to the third milliliters of a 1.53, remember capital M means molarity, NaOH solution to neutralize 1.87 times 10 squared milliliters of a HCl solution, what is the molarity of the HCl solution? So the first thing we do is, what are we being asked to find? Remember, capital M is molarity, HCl solution. What are we given? The milliliters of the base, NaOH, and its molarity to neutralize a certain amount of HCl. At neutralization, moles of base, moles of acid. And that equals milliliters of base times molarity of base equals milliliters of acid times molarity of acid. I forgot the bracket right here. Don't look, don't look. But anyways, let's put those numbers in. And what do we need to solve for? This, the molarity of HCl. How do we get it on one side? We divide by the number we're trying to get rid of. Anything divided by itself becomes number one, and it's gone. I like that. It's gone. Well, yes, I watched the Harry Potter movies over the weekend, always do when they're on. But anyways, so if I divide this side by 1.8 times 10 to the minus 2 milliliters, I have to do it the other. This cancels out. Molarity equals this number right here. And I do the math. And remember, on test 4, it will say, please use proper significant figures for all calculated answers, except for pH, is this whole numbers. Well, you can't have past the decimal, but I won't. And here I have 3 significant, 3, 3. The answer should have the same number of significant figures as the number with the lowest significant figures, 3. So that's 11.0, or it could be 1.10 times 10 to the 1 molar HCl. Again, when you see the word neutralize, that means titration. When you see the word neutralize, that means titration. I'll say that in slow motion. When you see the word neutralize, that means titration. And when you have a titration, you know, and this is given to you important information, test number 4, moles of base equal moles of acid, milliliters of base times molarity of base equal milliliters of acid times molarity of acid. And you put the numbers in, you solve for the variable by dividing what you're trying to get rid of on both sides, and that's how you do it. And I'd highly recommend you go back and look at problems 13 and 14. It's the same thing. All right, let's get into the fun part finally. Remember, I'm an organic chemist, so I'm biased. And that's the organic chemistry in this class. Organic molecules evolve around molecules that have carbon and hydrogens linked together in chains. They can be straight or branched. And you should know there's always 4 bonds to carbon. You should know that. So there's always 4 bonds to carbon. If there isn't, that's made up by hydrogens. Now, you should know, what is a hydrocarbon? That's a molecule with only carbon and hydrogen atoms. Gasoline is made up of mainly hydrocarbons that come from oil, which are mainly hydrocarbons. Molecules with carbon, hydrogen atoms. Now, you should know there are two types of hydrocarbons. One is a saturated hydrocarbon. What is that? Because the hydrocarbon is a molecule with only carbon and hydrogen atoms. And because it's saturated, it has in which all carbon-carbon, that's important, only carbon-carbon bonds are single bonds. Remember, single bond, one pair of electrons being shared. So saturated hydrocarbon, molecule with only carbon, hydrogen atoms, which all carbon-carbon bonds are single bonds. Unsaturated hydrocarbons, because it's a hydrocarbon, it's a molecule with only carbon, hydrogen atoms, but now because it's unsaturated, that contains one or more carbon-carbon multiple bonds, also known as double or triple bonds. And if you look at a carrot, the compound that makes the carrot look orange is an unsaturated hydrocarbon, beta carotene. And your body breaks that down to help your eyesight. All right, now, in organic chemistry, we have what's known as functional groups. Now, I'll never ask you what is a functional group, but it's a collection of atoms that react the same way. How do you find a functional group in a molecule? You look for what's different, what's not a carbon or hydrogen atom or carbon-carbon single bond. That's going to be a functional group and should get your attention like, not like that, but like this. That gets your attention. So look for anything that's not carbon or hydrogen or carbon-carbon single bond. And hopefully you've done this already, but let's go through a couple of these. This is from the practice problem answers in the Blackboard in the folder called practice problem answers. And you should know what a hydrocarbon molecule is, saturated hydrocarbon, unsaturated. You should know there are four, I can get that finger fixed once, 4 bonds to carbon. By the way, everybody see my college ring from Illinois Institute of Technology. Now, to know there are 4 bonds to carbon, let's skip this for a while. Let me come back to this in a little while. We're talking about functional groups. And if you take, when I teach 1212 at COD, which is organic chemistry, 1 semester, or if you need to take one semester, and it's not offered at COD, I also teach it at Elgin Community College. It's called Chem 170. And you need to find functional groups and name them. In this class, I'm not asking you to learn the names, but you should be able to circle them. How do you know what's a functional group? You look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like this. I love my whistles. The company that made this is no longer, was from West Germany. I've got 4 of them and they never leave my house. I think the last time I saw on eBay, they were selling these for like $25. Nobody's ever made a better one. All right, let's get back. Ooh, an oxygen bond to carbons. Functional group, it's called an ether. Ooh, another oxygen bond to carbon with carbons here. Functional group, that's called an aldehyde. Ooh, oxygen on this carbon, remember? OH, alcohol. Ooh, let's look at C. A nitrogen with carbons, That's a functional group. That's called the quaternary ammonium cell, which is near and dear to my heart because I have a number of patents in there. And that, being a world expert in that type of functional group, quaternary ammonium cells used for fabric softeners and antimicrobial products, things that kill nasty things like viruses, helped me make a lot of money over the years. Oh, here's another one, an amide. So you should be able to look for these and find them. Again, look for what's different, what's not carbon, what's not hydrogen atom, what's not a carbon-carbon single bond, should get your attention like this. Did I get your attention? All right, let's continue on with our review. All right, now, when you draw organic molecules, we normally, for this class, use condensed structures. And that shows the carbon atoms bonded together, but condensed the hydrogens on a carbon. And what you should know how to do is draw in the hydrogens for the following molecule. So how do you do that? Well, if we look at this first carbon, it has one bond to it, but there's always 4 bonds to carbon. So there's only one. 4 minus 1 equals 3. And that has 3 hydrogens, H3. We look at this carbon, and this one, same thing. Has one bond to it. This one has one bond to it. This one. So 4 minus 3, because there should always be 4 bonds to carbon, means I'll do this. Now let's look at that carbon right here. How many bonds to that carbon? Well, organic chemistry is real hard when I teach it. You have to know how to count up to 4 and know the numbers 1 through 20, which ones are larger and smaller. That's hard math. Anyways, this carbon with the right here has 1, 2, 3 bonds to it. But there's always 4 bonds to carbon. 4 minus 3 equals 1. So that has 1 hydrogen. If we look over at this carbon here, same thing. 1, 2, 3. So we'll have 1 hydrogen. And finally, the last carbon to put up is this one. If we look at that one, how many bonds to the carbon with the blue dot? 1 bond, 2 bonds. But there's always 4 bonds to carbon. 4 minus 2 equals 2. So that's how you put in hydrogens in a structure. And if we look at this problem, say 3 points each, drawing the hydrogens for the following molecules, you do the same thing. Now, if we look at C, this carbon right here, how come it doesn't have a hydrogen? Well, let's count the bonds to it. 1, 2, 3, 4. There's always 4 bonds to carbon. I can do it backwards, 4 bonds to carbon. Doesn't it look like it's 3D coming right at you? And there are 4 bonds to carbon. 4 minus 4 is 0, and that's why there's no hydrogen. The rest of those, just like I just showed you, that's how you figure out how many hydrogens are on there. And you should go through and work these before test number 4 this Thursday. You have plenty of time to do the problems on your own. Remember, if you have a difficulty, any questions, come to my office hours, or feel free to email me, or if there's time, email me and I'll see if I can set up a private Zoom meeting to help you out. That's the nice thing about Zoom. Now, when we talk about molecules, there are different ways to draw it. And one is showing the atoms like I just did. The other is called the line or stick method. And every bend in a line is a carbon, and every end of the line is a carbon. Now, for my class, for this level, for the rings called cycloalkanes, they're represented by polygons. Poly means many, gon-sided, many-sided things. And each bend is a carbon. So if we look at this molecule, it's a ring. This is called cyclohexane, which you don't have to know, but I'm going to write it down anyways. How many carbons in cyclohexane? Well, every bend in a line is a carbon. 1, 2, 3, 4, 5, 6. So there's 6 carbons in cyclohexane. This is called cyclopentane. How many carbons are in cyclopentane? I'm going to let you try one on your own first. Have some fun. Time's up. If you want, hit the pause button. If you haven't figured it out yet, now you can start it again. And there's 1, 2, 3, 4, 5 carbons in cyclopentane, this compound. Now, if we go into practice problems, organic chemistry for this, I ask you how many carbons are in the following molecule. And if we look at A, count the carbons, 1, not the hydrogens, 1, 2, 3, 4, 5, 6. Remember, the chemical symbol for carbon is C. Now let's look at B. What do I do? Oh no. Well, I count the carbons. This is 1, 2, 3, 4, 5, 6 here, but I have a ring. Each bend in a line is a carbon. So 1, 2, 3, 4, 5, 6. So 6 plus 6 is 12. And here's some more for you to have fun with. Now, if we look at E, you only count carbons, not oxygen or hydrogen. By the way, E is called ethyl acetate. It's one of the 2 molecules used for nail polish remover. The other is acetone. But here, how many carbons in ethyl acetate? 1, 2, 3, 4. And that's the skill you should have. Now, I only taught you 2 general reactions in this chapter. And the first one is, if you have a saturated hydrocarbon, a molecule with only carbon, hydrogen atoms, carbon-carbon single bonds, and you react it with the oxygen, and organic chemists are lazy. We don't balance equations unless we have to. And for my class, for organic chemistry, whether I teach it one semester just organic, or even my life, unless you have to, you don't. So when you react with oxygen, the two chemicals you get are carbon dioxide, CO2, H2O water. An important other thing is heat. And that helps drive your car, the combustion engine, heat your house, apartment, or condo by burning natural gas. Or if you start a fire in your fireplace, oh, that feels nice and hot, warm, combustion, that's where the heat is. Now, the other reaction I asked you to learn was hydrogenation. In fact, this was the first reaction I did research in when I started in the chemical industry after my PhD, and I was a postdoctoral fellow. And I looked at the hydrogenation of a certain molecule to be able to do those types at the company I work for. And you need a catalyst like platinum, palladium, or nickel. Catalyst makes something go faster, but is not consumed in the reaction. And anytime you have a double bond, hydrogen and catalyst, you break one of the bonds and each carbon gets a hydrogen. So if we look at the practice problems for organic chemistry, give the reaction product or products to the following reaction. Well, this is propane. That's the stuff you get in a white tank for your barbecue. That's how you make the heat to cook your stuff on your barbecue, like the good stuff, hamburgers, hot dogs, chicken. Now I'm getting myself hungry. Ribs, brisket. Oh, now I'm getting real hungry. I better stop. But anyways, propane plus oxygen. Well, propane is a saturated hydrocarbon, oxygen. I know I get CO2 and water. So the answer is CO2 and water. Now, if I take a ring, which is still a saturated hydrocarbon, I didn't put it down here, but that should be CO2 and water. Let's do one more. I'm going to let you try one. Let's share the fun afternoon. And your turn. Give the products of the following reaction. 3 points each. Ooh, I gave it away. All right, you need to hit the pause button or start playing. I'll do the problem. All right, how do you do this? You look at this molecule and you say, oh, carbon, hydrogens, carbon, carbon, single bonds. This is a saturated hydrocarbon. Now, what I'm writing here, you don't have to do this. You can do it in your brain, but I'm writing it out so you can see what's going on in my brain. That's dangerous, but important. And we're reacting with O2, and you should have memorized saturated hydrocarbon plus O2, and you should memorize gives carbon dioxide, CO2 plus water. Therefore, the answer here will be CO2 plus water. And you should be able to do that. You do not have to balance this. Just give the structures identity of the products. Now, there's one other reaction I asked you to learn, and that's this one, D, E, and F. You react this molecule with hydrogen nickel. Look for what's different. Ooh, a double bond. And anytime you have a hydrogen bond, a double bond with hydrogen and catalyst, where the catalyst can be nickel, platinum, or palladium, you break one of those two bonds and each carbon gets a hydrogen. And the rest of the carbons should also have 4 bonds to it. So this molecule, and remember, you break carbon-carbon single bonds except for combustion? No. So I have 4 carbons, I better end up with 4 carbons. I break the bond right here, one of them, like my general reaction shows me, and each carbon gets a hydrogen. And if I look at E, what's different? Double bond, same reaction, hydrogen, nickel catalyst. You break the double bond, but everything else stays the same, and each carbon gets a hydrogen. All right, now I talked about some things in the real world. What's a fat? It's a triglyceride that's a solid or semi-solid at room temperature. This is the industry I worked in. What's an oil? It's a triglyceride that's a liquid at room temperature. And I worked for a company that took fats, triglycerides, and made them into other chemicals to the tune of about 3 million pounds a week we did. Wow, that was a lot. And what we used at that company was tallow, also known as beef fat, and yellow and white grease, which was pig's fat. Now, how does soap work? Soap is an organic molecule or molecules, and they're called surfactants, which is short for surface active agent. I won't ask you on test, but I will ask you, how does soap work? And you should know, soap has a hydrocarbon tail or nonpolar tail and a polar head. Remember, like dissolves like. And water is polar. When you wash your hands, use soap and water. Now, dirt and grease are nonpolar. Know this. And they form a micelle, which looks like this. There's a part cut out so you can see inside. In the middle is a piece of dirt or grease. Know this. And let me go through this again. I think I'll be subtle. I get the message. You should know, leaving my class, how does soap work? And you should know soap has this structure, nonpolar tail, and a polar head. And water is polar, dirt and grease, I'll just put down dirt, is nonpolar. And you should know the important piece of the puzzle. How does soap work? is like dissolves like. Polar things are soluble in polar things. Non-polar things are soluble in non-polar things. Two together, non-polar don't mix. So how does water get the dirt off your hand? With soap. And you should know, you got a little piece of dirt on your hand. The soap looks at dirt and says, oh, you're non-polar. My tail's non-polar. It wants to be close to you, but the head wants to be far away because it's polar. Well, a lot of molecules of soap attach itself this way to dirt. And you should know this is a micelle. And now the dirt is surrounded by the soap, and the outside of micelle has the polar heads. And water looks at the micelle and says, I'm polar, you're polar. Let's go down to drain together. And they do, and that's how you got your hands clean. So let's go through this again, because it says on the screen here, hint, know this, it's important. How does soap work? You should know the structure of soap: non-polar tail, polar head. Water is polar. You use that to clean your stuff, whether it's your hands, your dishes, your clothes, your car. Same thing, works the same way. When I took my shower this morning, I probably was the only person in northern Chicagoland area thinking about, oh, look, I'm making micelles. And I was. Water is polar. Dirt is non-polar. Important piece of the puzzle. Notice the large font. Like dissolves like. And because of that, the non-polar tail is attracted to the polar dirt particles to form a micelle. And you should know what a micelle, how to draw. Now, water looks at the micelle and says, you're polar, I'm polar, because water only sees the outer parts of the soap molecule, the heads, which are polar. And the water says to the micelle, you're polar, I'm polar, let's go down the drain together. And they do. Now, when you use a towel, whether it's a paper towel or a regular towel in your bathroom, how does it get the water off you? How does it dry you? Well, here's cotton, which is also a form of this in paper too. And you see these OH groups, and they hydrogen bond to the water. And that's how you get it off. You should know, how does a towel work? By hydrogen bonding to the water. Now, one other thing I didn't mention, what's acid rain? Many years ago in the late 70s, early 80s, 1980s, my lifetime, yeah, I'm that old, don't tell anybody. But anyways, there was a serious problem, especially in the eastern United States. That was called acid rain. Acid rain, ooh, that means the pH is below 7. It's acidic. And when you have water that's acidic, it damages things like crops it lands on, you're trying to grow, fish in water, and it messed up a lot of things in the ecology. It turns out the sulfur dioxide coming from the coal plants that were used at that time would react in the clouds to make sulfuric acid, H2SO4, that would pollute the water that was coming down as rain. And they solved that by one, putting cleaners on the smokestacks of the power plants using coal, burning coal, and that dropped the level of sulfur trioxide, I think it was, that made sulfuric acid. And they shut down a lot of coal burning plants and have gone to better, safer forms of energy. You should know that. With that, we had a long session today. I'm done. I'm going to ask any students who are here to stay after so I can just talk to them for a minute or two. But I'm going to say goodbye. I'm done. You know what I'm going to do now? I'm going to say go in health in Yiddish, because my grandmother always said to me, "Gehen gesund." Goodbye now. I still laugh from Beverly Hillbillies. Granny, bye.